All right. So we're back. We wanted to talk a little bit about hemocyanin. In the last video, in the last lecture that we had together, we went over hemoglobin, and we kind of talked about hemoglobin a bit and kind of tied up some loose ends. We moved on to hemerythrin, and we talked about how we should start to look at the active site of different enzymes now as we come across them. And so we're going to kind of take those ideas, build upon them, and move into hemocyanin. Okay. Now, hemocyanin is a copper-based oxygen transport, right? That's all we've been talking about so far is just oxygen transport proteins. What's important to recognize, right, is that it's always important to look at the oxidation state of the metals, and typically copper is going to be found in the +1 and the +2 oxidation state. There are some examples. I know we won't talk about it, and at least in my time, I haven't really looked at it. But there are some cases where it's thought of, or we have seen, or there might be some evidence of copper in its +3 oxidation state. But like I said, that's a little bit beyond what we want to talk about. So for the enzymes that we're going to deal with copper-based, I think exclusively going to be looking at the +1, +2 oxidation states. Okay. Now, hemocyanin is a type 3 copper center. We talked about that, and take a look at your notes that you guys have. Or I also, like I said, there's a paper that I posted for you guys that kind of goes over this stuff too. But remember, a type 3 copper center, that means it's bimetallic. There are two coppers that are in there. And those two coppers, the two copper ions are surrounded by 3 histidines. Now, let me talk about this for just a second here. When they define these copper centers, they're defined by the ligands that are around them. So if they fulfill a certain, requirement of coordination sites, then they're going to be labeled as type 1, type 2, or type 3 copper centers. And so what I mean is this: if you take a look at some of the crystal structures, or the catalytic pathways, or the resting state of enzymes, you might end up seeing that there might be a water bound to some of these copper centers. Tyrosinase and what is it called? Catechol oxidase. Which, again, I'm just bringing stuff out of a paper. I'll show it to you guys here in a minute, right? What we'll see is that often water is kind of coming in and hanging out around the copper center, and then, as a substrate comes in, it displaces the water. So remember, one important thing to recognize is that since we are dealing with biological systems, right, obviously there's a lot of water around. Water is not a giant molecule, so it's, maybe not hard, but it's pretty stringent to exclude water, right? We have to have these hydrophobic pockets that get made and all this other kind of stuff, right? That's not too important. The point being, water, when you guys see it bound to a metal center, typically it's there as a kind of a labile ligand. Although in some cases we will see that water bound to a metal center actually is involved with the catalytic cycle, wherein an oxygen gets transferred from water to some kind of substrate. Okay, so we'll see that in a little bit when we talk about some of the other enzymes after we move through hemocyanin here. Okay, so anyway, the point being, that was kind of a long aside here. When we're looking for a type 3 copper center, we see 2 coppers that are close in proximity to each other, and we see them surrounded by 3 histidines. Okay. Now, hemocyanin comes in a lot of different forms. Okay, we have tetrameric, hexameric, and octameric versions of it. 4, 6, and 8. Just like what we talked about with hemoglobin, right? It was tetrameric. There's 4 subunits. These subunits cooperate with each other, and as soon as one binds oxygen, the next one's quicker, et cetera, et cetera, et cetera. The same thing is observed with some hemocyanins, although there are a lot of different forms. Just for instance, depending on where you get your hemocyanin from, some of them show a higher cooperativity than others do, right? So I don't know. For instance, if you get it from horseshoe crabs, they might be more cooperative than if you look from certain spiders or something like that. I'm not too sure. That's not too important either. But the point being, right, if you take a look at the subunits, right, each subunit's going to bind one equivalent of oxygen. So if we have an octameric structure here, then we can bind 8 equivalents of oxygen, and that can be used to transport, the oxygen around. Okay. But I know some of you guys talk about Hill constants and all this other kind of stuff in one of your other courses, and that's not really what I want to mention here. What I do want to talk about, and what kind of the focus is to take a look at how the metals behave in this system. And so here is a very, very generic description or drawing of what the active site for hemocyanin is. Right, we have two copper centers. Right, they are in proximity to each other, and they're surrounded by three histidines. Now, we always got to think about this, right? So whenever we see a new enzyme, right, what we always want to take a look at is, well, what's the same or what's different? How do we start to analyze these things? How do we start to look at them? And so let's go back to our buddy hemoglobin for just a minute, right? So right now, what we have drawn here is the deoxyhemocyanin. And that just simply means, right, we've got the resting state or the waiting state or whatever you want to call it, right? We just have hemocyanin that doesn't have any oxygen bound to it, okay? And so if you go back and you take a look at your notes for hemoglobin, right, the deoxy form of hemoglobin, right, the iron has five things around it, right? We had the iron center, we had the heme unit there, okay, that's got the 4 nitrogens that's bound to it, and then we had that distal histidine that was down here. Whoops. Okay, and so we had 5 things that were bound to that metal center, right? And that makes sense. We talked about coordination spheres and all that kind of stuff, right? Remember that we have to have an open site for the oxygen to come in to bind to the metal center, okay? If hemoglobin, for instance, had, the iron in hemoglobin already had 6 things around it, right? One of those 6 things would have to leave before the oxygen comes in. That would slow down the kinetics and all this other kind of stuff along the way, right? So one of the things to look at when you're examining a new enzyme or protein is take a look at how many things are around that metal center, okay? And so we can do the same thing here with hemocyanin. Okay, sorry about that. I had to load up some stuff that we're about to move over to here. So anyway, right, so as we were talking about there with hemoglobin, right, we're going to see this interchange between 5 and 6. And so when we're looking at hemocyanin, we see that there's only 3 things bound to the coppers right now, which means we do have quite a bit of space for other substrates to come in and bind to that copper. And what we'll end up seeing is copper, depending on the enzyme that it's in, we could see it, go all the way to a hexameric, we could see it go all the way up to 6 ligands around that copper. Although most commonly what we'll see is it'll start out at 3 and go to something like 4 or 5, okay? Now, what we're going to end up seeing in hemocyanin, and I'll tab over it here in just a second, we'll see it start out with 3 here in its deoxy state. And then what's going to happen is as the oxygen comes in, okay, the oxygen is going to bind in this kind of side-on manner here to both of the coppers, and that's going to distort the geometry around that copper, right? The histidines are going to start to move around a bit and to accommodate for that oxygen that's coming in there, okay? So let's go take a look at that real quick. This is in a, where was it? I just had it open, didn't I? There it is, yep. So this is one of the articles that I posted for you guys on Canvas. This right here, the oxygen binding and activation and reduction, right? This is a fantastic article that really, it doesn't go into too much detail, right? It's not an overbearing article, but it really talks about how oxygen binding happens in copper proteins. And, and so if you go through here, this is kind of a very good whoops, I did the wrong thing again. I did this in the last video I recorded. This page right here kind of gives a good overview of all the different types of, or a lot of the different types of activity that we end up seeing with these copper-containing proteins. If you look, we are down here and this coupled binuclear copper, right? There's hemocyanin, tyrosinase, and catechol oxidase. And what we'll end up talking about very briefly is that, well, I'll just talk about it right here, actually. The active site for hemocyanin is the same, nearly identical, what we see with tyrosinase and catechol oxidase. With respect to it being a type 3 copper center, it binds oxygen, and then the oxygen does something, okay? The difference being tyrosinase and catechol oxidase are not oxygen transport. As you can see, they're oxidase and oxygenase enzymes, okay? And I posted another article for you guys to read through about tyrosinase there, okay? But anyway, let's scroll through this here and get to the point that we want to make, right? So here's a good, catalytic cycle for, this is what this looks like, tyrosinase, I believe. Yeah, tyrosinase. So that's another good example there for you guys. Here's a good diagram that kind of talks about the ligands and how the oxygen binds to the copper centers, right? We see it uses the x squared minus y squared orbitals. We talked about those, right? And right here on this page, right, figure 5 is what we were talking about, right? Looking on the left-hand side, we see the copper centers there. They didn't draw the nitrogens in for the histidines, but they're at the end of those wedged and dashed and linear bonds there. Oxygen comes in, binds to the x squared minus y squared. There's a rearrangement, right? And over here on the right-hand side, right, there's the bound oxygen within hemocyanin, right? And so we see that the x squared minus y squared orbitals are the one that get involved in the bonding. There's a rearrangement, and we end up at a pseudo square pyramidal geometry. And the other point to pay attention to is look real closely. You'll see it starts out as a copper in its +1 oxidation state, and it's copper in its 2+ oxidation state over here. And so we do bind oxygen as a peroxo species, okay? So 2 electrons are transferred to the oxygen, so we are binding O2 2-, all right? And we talked about that when we talked about hemerythrin, okay? We said peroxides just loose and free in your body is not a good thing, right? And so we have to find some way to protect that. And so, we kind of see that we have to bury these oxygen transport, the active site for these oxygen transports with copper kind of within the subunits of the protein itself. The other way that we can kind of protect this is just, we bind the peroxide in a way that it's difficult for another substrate to kind of approach this. Unless we change the geometry around those coppers, which will happen in tyrosinase and catechol oxidase there, okay? So I don't want to intimidate you guys. I'm not saying you have to go through and read this entire paper and understand everything. What they talk about in here is just how they come up with these and all this kind of stuff. But this is a very, very, very good paper to kind of get a broad overview of what's going on, okay? So check this out, read through it, skim through it, at least look at the pictures and read the read the captions for that if you are doing nothing else, okay? And so from there we can move over here. This is the link that I posted for you guys in the chat, right, of the crystal structure of one of the, I believe this is just one of the subunits of some form of hemocyanin. Okay, so what I'm going to do is I'm going to get rid of the polymer there, right, and just look at the active site. So this is an oxygenated form of hemocyanin, okay? So you can see the 3 histidines there in the blue, right, the coppers are there in the orange, and then the oxygen in there is in the red. We can see that the oxygen is sitting outside of the plane that's formed by the 2 copper centers there, okay? And so this is about as clear a structure and a picture as we can get as to what it actually looks like in reality, right? If I bring back in my polymer here, right, or just the protein itself, whatever you want to call it, right? Right, we see this is very different looking structure from what it is with hemoglobin, right? That is kind of buried almost, we would say, in the middle there of this subunit, right, as opposed to with hemoglobin where the stuff was on the outside. And part of the reason is that just to prevent things from getting to that bound peroxide, I'm sure, right? Of course, there's some biochemist out there who's screaming something at me, or but that's okay, right? That's not too important. But anyway, so that's kind of all I really want to talk about with you guys about hemocyanin, right? We see right? We're looking at the oxidation state of the metals. We're looking at the coordination of the metals, what ligands are around it. We're looking at where it is within the structure itself. Is it buried? Is it near the surface? We're looking how the substrate is bound to the metal center, right? And we're looking at how the geometry changes. Are there open coordination sites, right? All these different things that go into building a story about how does this active site work, okay? Now, when I've been talking about active site this whole time, right, it's a little bit different here, right? So this kind of wraps up the oxygen transport part of what I wanted to talk with you guys for this course, because all we're doing with the oxygen transport is oxygen comes in, oxygen leaves, right? Oxygen comes in, oxygen leaves. What we're going to talk about next is now we're going to bring something in, do some kind of transformation at the active site, and then kick off a substrate, okay? So we're going to move a little bit more into what probably would be a better definition of the word enzyme, right? So we'll talk about that, and that's it for this video. So I will see you guys in the next one.